Like me, you probably, well, and by that I mean you cannot install an ad blocker on your work computer. You probably feel like the universe sends you a lot of signs. Many of those signs have to do with purchasing decisions. So sorry to burst your bubble, but it's not the universe, it's us and people like us. So it's the ad companies. So today we'll tell you about how we at Criteo are using deep learning to power the predictive bidding engine. And in order to do that, I want to first explain to you what I mean by bidding in this context. What are some of the challenges that we are facing? What do these bidding models look like? So what goes in, what comes out? Some details about the architecture. How long does training these monstrosities take? Our tech stack that helps us in the process, and finally some conclusions about where we are with that today. Okay, so what is bidding? Now, let's say you go like on CNN.com or whatever is your favorite type of news, and most likely you're going to see some ads. Now, a disclaimer, I don't actually know whether CNN is a client of Criteo or not, but okay, let's say here the ad actually worked out pretty well because I'm really looking forward to the 5th season of Stranger Things, and this reminded me of the fact that it's about to come out. So here there are two kind of main sides in the equation. There's the publisher, so in this case, the publisher is CNN.com, and then there's the advertiser, which in this case is Meta. Now, if you were, say, on Facebook or Instagram, then it would have been the publisher who is Meta, and then the advertiser could have been anybody else, including Meta. Now, in addition to the kind of obvious players, the publisher and the advertiser, there are also intermediaries, such as Criteo, who compete for the ad placement on the publisher's page. Now, this is something that is really done on a per impression basis. So every time that you're about to load a page that has ads, this is the time when we decide, how much we're going to bid for this spot on this page for this person. So that is something that is called real-time bidding. Now, something that is tricky about it is that we have to, bid when compose the ad with the right products and put it in front of you all in the time that it takes the page to load. So the whole thing, like all of the steps involved and some others I didn't mention, we're talking about hundreds of milliseconds. For our part, for the bidding, it's actually much lower than that. The latency constraint is like up to 10 milliseconds. And I think I'll have that number again somewhere on the slides. But basically, this is kind of the big context of what I'll be talking about. So the question that we're trying to solve is how much should we bid? Because, of course, the advertisers are willing to pay a certain amount for the ad. And we're the charity, we do want to make money, so there's a margin. We, basically that's where our profit comes from. So if we bid too low, we won't win. So there will be no ad, no money to be made. If we bid too high, okay, that's also rather suboptimal. There's a big formula for what we refer to as eCPM, expected CPM. A big part of this formula is something called CPA, cost per action, times the machine learning model prediction. And yes, I know here I use CPM, so cost per mile. This is for historical reasons. Even though we do it on a per impression basis, it's just much easier to pronounce numbers that are, 1,000 times that. Okay, so cost per action, this refers to the cost that the advertiser is ready to pay. The action could be a click, it could be a visit, it could be a sale. So that depends on the campaign goal. So it's something that is defined by the advertiser. And finally, the prediction, this is the part that is interesting to me because that comes from machine learning models. This is the probability of the action given a display. So given that we do win the auction and we get the display, what is the probability that a desired action is going to take place? Yep, that's where the bidding machine learning models come in. So what are some of the challenges? Well, I already mentioned one of them, but let's talk a bit about the data. The good news is that we have a lot of it. Now, the bad news is that we have a lot of it because, yes, it's good to have data, but then it's also a bit tricky to train models on data sets of this size. So typically, we train our models on multiple weeks of impressions for some geographic location. So something that is usual to have as a data set size is billions of rows, and each of those rows has hundreds of features. Most of those features are categorical. Many of those categorical features have very, very high cardinalities because, let's say, the URL of the publisher is a feature, and as you can imagine, there are many URLs in the world. Then, of course, you have the advertiser, the campaign ID. There are also many different campaigns. So we have some categorical features whose cardinalities are in the hundreds of thousands. And then finally, there's that detail I mentioned about how, okay, we are doing 10 million plus inferences per second. And yes, the serving latency has to be under 10 milliseconds for the real-time bidding. Some additional challenges are the fact that it's not like you train the model and you're all set for the months to come, because as I mentioned, say the URL of the publisher is one of the features. There are different websites appearing all the time, so those modalities don't show up in your categorical data that you trained on, so you have to retrain the model. Then you launch a new campaign, that's another modality. If you don't retrain the model, all of those new modalities will just show up as kind of rare or unknown, which is not very useful. So the performance of the model is going to deteriorate pretty fast unless you retrain. And then, of course, you have your usual suspects. There's missing data and severely imbalanced data sets because, again, as you can imagine, how many times do you click on an ad that you see, and out of those times, how many times do you actually buy something? Okay, so what do these bidding models look like? So you have the machine learning model, and going into that, you have some inputs. So I roughly divide them into 3 categories. So there's the shopper intent. This comes from the user, third-party cookies, if there are any available. There's the advertiser data, so everything about the advertiser, the campaign goals, etc. And there's the contextual data. Contextual data is mostly the publisher, so what kind of website is this? But also things like, what time of the day is it? What's the day of the week? Where are we geographically speaking? So all of these things go into the model, and it produces the probability of, let's say, a click or a sale or a visit. So again, this depends on the goal of the campaign. Now, historically, these kinds of models were mainly logistic regression and gradient boosted decision trees. So there was some very heavy feature engineering that was necessary to make them work well. And also, historically, there would be a separate machine learning model per goal. So there would be a separate model for click, a separate one for visit, separate one for sale. You need different people maintaining them, training them, etc. Now, what has been happening very recently, I'd say the past couple of years, especially picking up the past half a year or so, is that we have been replacing these linear models with deep learning models. So now there's no need for feature engineering, so yay. Another big shift is that we have replaced, or are in the process of replacing rather, this single model per task paradigm with multitask learning. So in multitask learning, you have a single model that is going to make multiple predictions given the same inputs. So the same model will give you the probability of a view, of a click, or a visit, or a sale. So I'll talk about that in more detail. Okay, so what do these models actually look like architecture-wise? So first, of course, you have the inputs. There's some pre-processing to be done. So as I mentioned, many of our features are categorical. So okay, where missing is a special category. Missing, or let's say unknown, that's another special category. So these features are first one-hot encoded, and then they are embedded. And then all of the feature embeddings are concatenated into a single input feature embedding vector. What we sometimes do after this is that we take this concatenated vector and we project it into a lower dimensional space. We don't always do this. When we do, we found that it doesn't hurt the performance and it helps to keep the model size under control. So just a little tip if you're suffering from having lots of data, lots of categorical features. Now, then comes what is probably the most interesting part, the backbone model. Here we tried a variety of architectures, transformer-based ones that come with all sorts of gated units, DCNs, deep and cross networks, and things that are kind of more vanilla, like MLPs with residual connections. I'm not supposed to say, what is the architecture of the model that we have on prod right now, but I can just tell you, as somebody who trained these models, is that careful optimization of the hyperparameters seems to be more important than the actual architecture that you choose. So if you tune the hyperparameters on an MLP with residual connections well, it will probably perform as well as something that is much fancier, like a DCN network. Now, multitask learning. Multitask learning is a bit of a game changer for us, actually. So here, some of the layers are shared. So of course, the embedding layer is shared because if you are not sharing the embedding layer, what are you sharing? You just end up with separate single task learning models. Then some of the layers are going to be distinct. So the backbone following the embedding layer, this could be shared between all the tasks, or it could be distinct. Kind of depends on the scope, etc., that you're doing. And then the prediction heads are going to be different per task. So here, typically, we have an MLP that we just refer to as the head, the prediction head, following the backbone. So those are all going to be separate per task. Now, your loss is going to be composite, made up of terms corresponding to each of the different tasks, and you can balance the losses using the weights inside the loss. So that's pretty straightforward. It just means that you have more hyperparameters to tune. Also, your loss is cascaded because, of course, you cannot have a sale unless you had a visit, and you cannot have a visit unless you had a click. So, when your batch of data comes in, you have all the impressions, some of which have been clicked on, some of which have been visited, etc. So what we do is we basically multiply each term in the loss by the label of the kind of preceding step. So this way you're not trying to find the sales between all of the pages that haven't even, all of the impressions that haven't even been clicked on. Then something that we also found to be helpful in the context of MTL in particular is to have different virtualizations and different dropouts on the different heads, because what I just mentioned about the cascaded loss, with that you end up with very different effective batch size per task. So of course your largest batch size is the one that corresponds to has there been a click on this display, and then your smallest batch size is has there been a sale on this display. So because the batch size is different, you need different amounts of regularization per task. Now, the advantages of MTL, there are many, but okay, I'll just state some obvious ones. So first of all, you have a single model to support instead of a bunch of them. You're also replacing a chain of models with just a single model, because previously, if your campaign goal was to predict the sale given a display, you actually had to get the inferences of all the models in between. So prediction of sale given a visit, prediction of visit given a click, click given a display. Now you just have straight away your prediction of a sale given a display. So that makes things much easier operationally. And something that, to me as an engineer is probably the nicest thing about MTL is that, so you have these much less frequent events, such as sales, and then you have much more frequent, although still pretty rare events, such as clicks. And you can leverage the data from clicks when you're training the model for sales, because in the end, the embedding layer is shared between the different tasks. So that has been nice. How long do these models take to train? So this course, kind of depends because we do separate our models by kind of geographic areas, let's say. So depending on the area, basically depending on the area, you have different dataset sizes. And depending on that, of course, you have different times that it takes to train your model. But roughly speaking, we're talking about something like 10 to 15 hours of training that is distributed among 4 H200 GPUs that are on the same machine. If they're not on the same machine, it takes much longer. So just try to put your GPUs close. We optimize the hyperparameters so that we have large mini batches. So typically, we're talking hundreds of thousands of rows in each mini batch. One of the challenges that I mentioned was the fact that we have to frequently retrain our models. Some models are retrained once a day, then other models are retrained more often than that. So if your model training takes 10 to 15 hours, and God forbid it fails and you have to retrain, that can be an issue. So what we do instead is we use something that is called continual learning. So in the continual learning, we have a pre-trained model. And then we have the embedding layer that is partially pre-trained on all the modalities that were present in the original training data. And then you fine-tune on new data, so you have new modalities. And for those new modalities, the embedding tables are going to be initialized from scratch. Now, our tech stack, so for scheduled trainings, we use something called Ray. We use Ray data for data parallel training. We use Ray train. These things are deployed on Criteo's on-premise Kubernetes cluster. And then once the model has been trained, we export the PyTorch model because, yes, did I mention we use PyTorch, and then we export it and the pre-processing as a single graph into ONNX. And once we have that, here comes the time for inference. We use Dynamo, Triton, NVIDIA inference servers. Those are nice because they allow for dynamic batching. So I mentioned a few times already the latency of 10 milliseconds. So we don't really have time to sit around and wait to batch the data for inference. So in dynamic batching, we usually succeed to batch it into, say, sets of 2 and 3. That still helps quite a bit. Now, where are we with all this today? We found that deep learning models significantly outperform, the historical cousins like logistic regression and gradient-boosted decision trees in offline metrics. And then, of course, we had to do A/B tests, and we found that these deep learning models also bring a large uplift online. And they're now being gradually rolled out in production. So more signs from the universe to come. Thank you for your attention.